Hey everyone, welcome to another lecture of digital signal processing. In today's class, we're going to see how to compute your discrete Fourier transform in a faster and efficient manner. So, why this is required? So, in order to understand this, let's look at the number of multiplications and additions required in your normal computation of so for a normal DFT, as I have shown you in my previous video, for a 4-point signal, you require 16 multiplications and 12 additions. So in terms of n, if I am taking the signal to be of length n, so that 4 to 16 means my n-point signal requires n square multiplication. And for the 4 to 12 addition, my n-point signal, its equivalent is n square minus n. So this is quite extensive, or this is quite big when you think of the number of samples your audio must contain. Because we are talking about, let's take a music song or a music file which is for 3-minute duration, and in this 3 minute, you're going to take, let's say, a low sampling is at 8 kilohertz, which means you're selecting 8,000 samples in 1 second, and that converted into 3 minutes, that's going to be a lot. That's going to be around 1,000 k samples. And if you want to do any kind of frequency filtering to these samples, you need to convert these 1,000 k samples to a DFT representation or a DFT form, which requires you 1,000 k square. So that means that's a lot of multiplications, and it is not an efficient manner or efficient computation that we want. So now we will be looking at how to reduce these number of multiplications and additions using your faster computation. So I am writing the DFT and IDFT multiplications and additions that go. And for my IDFT, I'm going to just include a plus n, that is an extra term, which is because of the scaling 1 by n, which is present in my inverse discrete Fourier transform, and which is absent in your DFT. Good. So the class of algorithms that deal with the reduction of these number of multipliers and adders for Fourier transform are termed as your fast Fourier transform. Okay. So in case of fast Fourier transform, there are different classes of algorithms. So there are like 3 to call, which out of which 2 we'll be discussing in this lecture. The first one is your divide and conquer approach, and the second one is your radix 2 FFT or radix 2 algorithm, and the third one, which we'll not be discussing here, is your radix 4 algorithm. So I would say around 80% of the systems, 80% of the filters that work on DSP with Fourier transform are built using your radix 2 algorithms. So radix 2 is one of the most widely used fast Fourier transform. So we'll be seeing that in detail. But before we get to that, we still have a divide and conquer approach to see, which is also pretty useful if you get to know it. So the idea is very simple. So in divide and conquer approach, what we are doing is we are going to factorize your signal. So you have an, let's say, 6-point signal. I'm going to factorize them into 2 and 3. So 2-point and 3-point. And then what I'm going to do is I'm going to compute the 2-point DFT 3 times. Then I'm going to compute the 3-point DFT 2 times. So it's, I don't want to over confuse you at this point. Let us just say like my 6-point signal is factorized into L and M, which is 2 and 3. And now I am going to derive a means to compute my 6-point DFT in terms of these 2 and 3-point signals. So I'm going to compute my 2-point DFT and I'm going to compute my 3-point DFT, and I'm going to make sure that that is going to be equivalent to the 6-point DFT, but in a lot efficient manner, which means it requires the one on the right hand side, the factorized form must use lot less multiplications and additions when compared to the LHS or the unfactorized signal. Now, whether this divide and conquer approach is restricted to only non-prime numbers, because when it is a prime, you can't do factorization, it doesn't matter, because when you have a prime number, you just do the zero padding and you can go ahead with factorizing. Okay, so just that is there is no restriction for this algorithm. So now we are going to see the first step was factorization of n to l and m. So now that is your first step, and your second step is now we are going to store our one-dimensional signal as a 2D array. Since we are factorizing a one-dimensional signal of length n into L into m, so we are going to store it where my L represents the rows and the first factor represents the rows and the second factor represents my columns. Understood? So now that is how I'm going to store it. So my L represents the rows and M represents the column, and my indexing is 0, 1, 2, 3. So here in this case, if it is 2 and 3, my L is going to be just 0 and 1, and my M is going to be 0, 1, 2, right? Because that is what 2 and 3. But I'm going to represent, I'm going to draw a general matrix here, a general two-dimensional matrix that should explain how we arrange or how we place this signal, which is of length n, in a 2D form. So we can place this x of n into the matrix on the left hand side by two ways. I'm calling it as a row transform and a column transform. So let me first write the row transform. So as m rows at a time, so that is given by ml plus m. So there are two m, so don't want to confuse you. So capital M into L plus m. And I can also place this x of n as a column wise operation as L columns. That is given by n is equal to L plus m into capital L. So this is how I'm going to reorganize my one-dimensional array into this two-dimensional matrix. Good. So you can plug in some values and see how it goes. For n is equal to 0, right, and L and M equal to 0, what do I get? You can just put these values and you will see you're going to get it as x0, x1, etc., x of m minus 1. So the row representation is given in the first diagram. Good. So just put L is equal to 0, M is equal to 0, and L is equal to 1, and M is equal to 0. I get my M. Okay. Just plug in these values for my L and M. So then I could have written that as a small l and small m if it is not too confusing. So the column wise, so I am filling it as L minus column at a time. So you can see I am taking my rows is shown in yellow color and my column wise is shown in a bluish color. So these are the two ways I can organize my one-dimensional array. This is let me just we are looking at only the theory of this at this point, and when we cover some numericals, it will be more clear on how this is getting done. So for now, I think this should be clear. This is filling it as L columns, and here I am filling it as L rows, which means I first fill the columns and then I go on. Here I do it row wise. That is what it is. Good. So now let me take you to step 3. So the step 2 was 1D to 2D transformation, right? So it's a mapping operation where we took our 1D matrix and we arranged it into a 2D matrix, either in row-wise transformation or column-wise transformation. So in your row-wise transformation, you do rows at a time, and in your column-wise transformation, you do one column at a time. Good. Now, for the DFT also, you have the same provision of representing your DFT, which is a one-dimensional DFT of length n, into two-dimensional form as a row-wise and a column-wise operation. So your row wise operation for k is given by mp plus q. So here your L and M are replaced with indices P and Q. So we are using different index for my Fourier transform. And for your column wise operator, your K is going to be equal to QL plus P. So that's going to fill it L columns at a time. So here what is important is the factorization that we have done on the time domain, N is equal to L into M. That is also applicable at your DFT level. So which means my K is also, the factorization is applicable here also, and that is what makes me write this row wise transformation and column wise transformation. The step 4 is now the DFT formula needs to be modified. So the DFT formula, which is for the unfactorized signal of length n, must be now modified for the signals of length of factors L and M. So we need to now adapt, we need to modify or adapt our algorithm to this factorization and make sure that through this factorization, two things are achieved. One is the simplification of the number of adders and multipliers, and also the output that is coming after this simplification or after this rearranging through factorization must be the same as what was done previously, right? So we cannot alter the values. The output should not change, but the process has to be simplified. So that is the goal. We are trying to simplify the DFT computation process, and that should not alter your output. So now what all assumptions we are going to use from previous steps 1 to 3 is, I'm going to take my factors n equal to ml, and then I'm going to assume my input signal is filled, or the mapping for my input signal is column wise, and the mapping for my output signal or the Fourier transform is row wise. All right. Now I'm going to use this and I'm going to write my updated Fourier transform. So now my Fourier transform equation is going to look something like this. It's going to say x of L comma M, because I am having factors L and M. So it is now a two-dimensional Fourier transform. It is no longer a one-dimensional Fourier transform. It's a two-dimensional Fourier transform. And I'm going to write Wn of k and n. My k is now mp plus q, and my L is now n is now ml plus l. All right, so this is the updated Fourier transform. It makes sense because now we are having two factors m and l, which means I need to have two summations, sigma l equal to 0 to capital L minus 1 and sigma m equal to 0 to capital M minus 1. So this is the factorized Fourier transform. So x of n, when you factorize it, you end up with the terms x of L comma M. Good. So n tends to give you Lm. So far so good. So that was your step 4, and now we are looking at step 5 in our divide and conquer approach, is to simplify this updated Fourier transform equation. So we are going to go for the updation, and always whenever I'm telling you simplification, so here I'm talking simplification, and that happens always with your complex exponential. So here also I'm having Wn to the power of mp plus q plus nl plus l. So I'm having a big term which is associated with my complex exponential, that is my w. So I am going to simplify this, and this simplification means I'm going to first expand this and see what all terms can be grouped, some of the terms will definitely become 1, and what remains. So we'll just see what all things we can do with this. So I'm seeing in my first term capital M and capital L. So that will give me n, right? N is equal to M into L. So that is the simplification that goes here. All right. And then what I am going to see here, let us see. Yeah, I think except the last term, which is Wn to the power of QL, all the other terms can be simplified. So that is, now what I've done here, I brought my M down, I brought my L down. How do I do that? So I'm going to show you how I have written this next step. And let me just show it on this side if you're, if it is not very obvious for you. So this is my e to the power of minus 2 pi by n mpl, and I can just rearrange it slightly. I can write it as n by m into pl, and this becomes my wn by m pl. That is what my second term is, and the same way I can write my third term. And now I know my n by m is equal to L, and my n by L is equal to m from the factorization. And this is 1 because it's a multiple of n. So it's a single integer, it's 1 multiple of n. So wn to the power of n is equal to 1. So we have seen many places whenever it is a multiple of n, it becomes 1. And now I am having just 3 terms. All right, good. So now I can tell by just seeing this is the simplified complex exponential. The first one has to do with my sigma L, right? So that will be taken with my sigma L, and the second will be associated with my sigma M, and the third one is just left on its own. It's just going to be a multiplier in my simplified equation. So let me write my simplified equation. I'm by regrouping the sigma. So I'm taking my sigma M, right, x of L comma M W M M Q, good. Okay, so now what do I have? So this is my, what I see, my inside summation is my M point DFT, right? And my outside summation is my L point DFT. So your divide and conquer approach is basically doing what? An endpoint DFT as your M point DFT and an L point DFT, and that multiplier there, which is your Wn of LQ, right, takes care, that is just with an extra multiplier. You can say like I'm doing my M point DFT and my L point DFT with an extra multiplier Wn to the power of LQ. But now here, another thing you need to know is now we are going to do the computation. We are going to see how many. So this is my divide and conquer DFT. So I have modified my original DFT into my divide and conquer DFT, and I want to see in this divide and conquer DFT what is the advantage. Have I succeeded in reducing the number of multiplications and additions? So that is what I want to check here, and I'm going to check that by taking. So let me say for my M point DFT, normally I require M square multiplication and M square minus 1 additions, right? So that is what is required. But now the thing is, you need to check this x of L comma M. So I means if this is a row wise, I've told you this is my row wise operation, and when I do it row wise, I'm filling M rows at a time and I'm doing it L times. Right, very, because this has to be L times, so which means I am doing my M point DFT L times because of x of L comma M. Just for now, understand that it is a two-dimensional, so my M point DFT is being done L times. So my computation is now Lm square into L into M square minus M, because I am filling these M rows L times, so that is why I am putting it as L into M. Good. So if it is at this point, if it is still not clear, just wait for the example that I will be showing you next, and this should come clear why we are multiplying with L. And then next is our scalar. I would say just a standalone multiplier Wn to the power of LQ, which is given by Lm multiplications. So which means that is just, it is multiplying your L and Q, which is for L and M times. It is multiplying. You can see it in many ways. It is multiplying with each elements of the M point DFT, right, which is computed for L times. So it is just Lm multiplications. It will add to your computation steps, because it is multiplying with all values of x of L comma M. Next is for your L point DFT. Yes, now you can tell me for my L point DFT, I'm going to see what I will need is I am going to do my L point DFT m times. Good. So for my L point, I'm going to have L square and L square minus L, but that's going to be performed m times. So I'm going to have, okay, so that is because it is my column filling. So I'm filling the columns one by one, but I'm filling the columns for m times. So that is why it is m L square. I know it's not, it might not, it might not get through to many at this stage. So just wait and see the example and you will be, at least this should be clear. I'm pretty sure this M point and L point is clear for everyone. Only that why we are multiplying with L at M point and here we are multiplying with M for an L point. So that part, I think only we can show it in an example. Now I have all the stages computation. What is the overall computation of in terms of multiplications and additions? I'm going to add it all. So for my multiplication, for the first, I am having Lm square. For the second, scalar multiplier or standalone multiplier Lm, and now plus ml square, which simplifies to Lm into m plus l plus 1, which is equal to n into l plus m plus 1. For the total number of additions, I am having Lm square minus Lm, right? Minus. So this is your total number of additions. There is no addition for the standalone multiplier, so only these two terms, and then that simplifies to, right, the same way you can, it is minus Lm, so that becomes minus 2 Lm. So this becomes Lm square plus ml square minus 2 ml, or I take my Lm outside, m plus l minus 2, or n into m plus l minus 2. Excellent. So now let us see how the computation has improved. So for, let us say for an n point, let us take an example. N is equal to 8. Normal DFTs, I require 64 multiplications and n square minus n, 8 square minus 8, 56 additions, right? This is the normal DFT computations. And now what will happen in this divide and conquer approach? So in the divide and conquer, if I have to compute, I'm going to compute 8 into, so I have to factorize 8. So what will be the factor? 4 into 2, yeah, 2 into 4. I'll use it as 2 into 4. And now my computation becomes, for multiplication, I'm going to 8 into 2 plus 4 minus 1, right? And that is 56. And for addition, my computations are 8 into 2 plus 4 minus 2, that is 32. Oh, good. Excellent. So now you can see there is a reduction, right? 56 has come down to 32 and 64 has come down to 56. Not much. So that is why divide and conquer approach was a primitive way of doing. I would say it comes before radix 2. So radix 2 is the next algorithm that we'll be seeing, which is an upgrade of divide and conquer and much better performance in terms of this speed. That is reduction in the multiplication and addition. So let us see. So this is your divide and conquer, which is also very important to know, and it's a very the idea is very novel and it is very interesting to learn. So now we will see an example for your divide and conquer approach, and in this example, what do we have? N is equal to 15, and that is factorized into 5 and 3. And now this is my 2D representation. I am writing the matrix here. I am writing my LM matrix here. I am writing it as how? Column transformation, right? I am writing first column 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, 11, 12, 13, 14. I can write it in any way. I can write it as 0, 1, 2 in the row wise, and I can write it in, here I'm doing column wise. I can do it row wise also. I leave that, if I do it, I leave that as an assignment or take home for you. I'll show here that I'm doing it. These are the rows and these are the columns. Okay, so I'm having 3 columns and I'm having 5 rows in my 2D representation, or I would say that is my 1D to 2D mapping. So my input signal is a 15-bit long or a 15-point signal, and that is now factorized into 2 signals of 3 and 5 point. And now I have organized this into columns. So if I am doing the columns first, right? So the ordering is very important. So you can just remember this example, and I want to just go with this because there's another way to do this, which is start, this is the column and that is a row. So but it gets a bit confusing if you see both at the same time. So let us see this first, how we do it. So we have arranged these values in column. We have arranged it in 3 columns. You can see the sequence 0 to 4, 5 to 9 and 10 to 14. And after we do that, what we are doing is we are now computing the 3-point DFT row wise. So because I am factorizing it into 3 and 5 point, so I have to find the 3-point DFT, and you just see here how many times I am doing the 3-point DFT. I am taking the 3-point DFT 5 times. So that is what is your L in the computation. So now the computation will be multiplied with 5. 5 into 3-point DFT, right? So that is what you are doing, the 3-point DFT 5 times here. And after you do that 3-point DFT for 5 times, you're multiplying it with your standalone multiplier, W15 to the power of L cube. And that is now your right. And after that, you're doing the 5-point DFT. So you have done with 3-point DFT, you have done with the standalone multiplier. Then what's left to do is your 5-point DFT. And the only way you can compute the 5-point DFT is to group them vertically. When you group it in vertical or when you group it in column wise, that is where you can find the 5-point DFT. And here you're computing 5-point DFT how many times? 3 times. See? You're taking 3-point DFT for 5 times and you're taking 5-point DFT for 3 times. That is what that multiplicative factors of L and M are doing in your computation process. If that was not clear back then, it should be clear for you by now, right? So this is an example that should clear all your doubts that you had or you were having while doing the previous explanation. The previous steps, if you had any doubt, that should be clear. And the ordering of your Fourier transform, your 15-point DFT is horizontal or is row wise, because your input signal has been arranged column wise. Your output DFT is arranged row wise. Important, right? It is vice versa. If that was row wise, this would have been column wise. So not to confuse you much, I'll just say since the input signal was arranged in column wise, the output sequence or the output FFT or the Fourier transform indexing will be row wise. You can see x0, x1, x2, x3, x4, x5. So the indexing is in row wise as you see. And that is your 15-point DFT. So your 5-point DFTs are the values after multiplying with the standalone multiplier, right? I have written is using the same notation, so just it should not be confused. I could have used a different notation, but then that would again be hard to interpret. So I have kept the same groupings and same notations to make it very more understandable for you. So as you can see, 3-point DFT is computed 5 times and your 5-point DFT is computed 3 times. So that is your divide and conquer approach. So we'll be